Hey guys, this is Romit, the actuarial guy. How are you doing? Today we talk about subject CD3 and I'll be discussing a few topics from subject CD3 that I got a few queries on. So some people asked me to discuss a few topics from subject CD3. The first one of them is a very interesting, very important topic called as Central Limit Theorem. The concept of central limit theorem lies in something called as the law of large numbers. The law of large numbers. Okay, so what do we mean by the law of large numbers, and the central limit theorem is what we are going to discuss today. Okay, so what central limit theorem says is that if I have a bunch of independent and identically distributed random variables, say I have got IIDs x1, x2, x3, x4 up till xn. Okay, so I have these bunch of independent and identically distributed random variables, and if I add them up, if I take the distribution of sigma xi, where I goes from 1 to n, the distribution would be a normal distribution. That is what the central limit theorem or the law of large numbers says. How do we interpret this? How do we understand this? I'll take an example. Okay, I'll take an example of this thing. So, for an example, let's consider the nature of these random variables. These x1, x2, x3s, all of these. Let's assume them to be a trial, a Bernoulli trial consisting of a toss of a coin. So I'm talking about the toss of a coin wherein I can get either a head or I can get a tail. So I have two options. I can get a head or I can get a tail. Obviously, it's an unbiased coin. So the probability of getting either a head or a tail is same. It is 0.5 for both of them. Okay. So if I talk about this, if I consider this, these trials, these tosses of coins are all independently and identically distributed. They are independent because one toss does not influence another, and each one has the same distribution. Each toss has a probability of 0.5 for a head and 0.5 for a tail. So they are identically distributed. If I toss this coin, let's say I toss it 5 times, I can get a head or a tail each time. So in the first 5 tosses, I can get something like this. I can get a head first, and then I can get a head again, and then I can get a head again, and then a tail and a head. So if I have no other knowledge about this coin and I will see this distribution of these 5 tosses, it will make me believe that it is more likely for me to get a head on this distribution. That means that there is an element of biasness here. That means that I will be made to believe that there is some sort of randomness involved. That I can get a head more number of times than the number of tails, even though the coin is fair. What this distribution tells us that I can get heads as much as 4 out of 5 times and a tail 1 out of 5. So this is some sort of randomness which is causing this, distribution to be quite biased or uneven. But instead, if I toss this coin 1000 times, we will see that this randomness will somehow get cancelled out. For example, even if I get 5 heads in the first 5 tosses, in 1000 tosses, I will expect to get 500 heads and 500 tails. because ultimately this coin is not biased, it is an unbiased coin. And over time if we take a lot of tosses, this randomness will go, and this element of biasness will disappear, and this will make this distribution somewhat normal. So when I toss the coin a large number of times, the distribution tends to be normal. You can even try this. If you toss the coin a large number of times, you will get some numbers like you might get 480 heads and let's say maybe 520 tails or something like that. Some figures which are close to this 50-50 ratio here. So this is what happens in the long run, or when there are large numbers operating. For a large sample, the independent and identically distributed random variables tend to a normal distribution, and that is what the law of large numbers says. So in general, if I have a large number of tosses or a large set of variables, and if I take their sum, the sum sigma x, where I goes from 1 to n xi, will tend to have a normal distribution with a mean n mu and a variance n sigma square. Can I prove this? I want to prove this to you guys. So I will give you a proof here. So if I take a proof, if I talk about the distribution of this thing, if I want to find out the mean of sigma x, I need to find expectation of sigma x. This would be nothing but expectation of x1 plus x2 plus x3 plus x4 going up till xn, which would be the same as because I can just separate these expectations, because that is how expectations work. This can be expectation of x1 plus expectation of x2 plus expectation of x3 going up till expectation of xn. In the next expression, I know all these random variables have the same distribution. So I can write all of them as expectation of x, because I would expect them to be same regardless of which x it is, because they are all identically distributed, so they have similar expectations. So I can write this as because xi's are identical. So this happens. So I can now add them up, and this becomes n times expectation of x. And as the mean of each xi was mu, thus this is equals to n times mu. So I got the expectation. Now talking about the variance, a similar proof is possible for variance. If I talk about variance of sigma x, this would be variance of x1 plus x2 going up till xn. So as they are independent, this implies that their covariance term is 0. So variance of all this would be variance of x1 plus variance of x2 up till variance of xn. The reason for this is that variance of x1 plus x2 is usually equal to variance of x1 plus variance of x2 plus 2 times the covariance of x1 comma x2. So this is the formula, but since these are independent terms, this term goes away. So I can just cancel this thing out, and I just have the added variance of the two terms. So as these are independent, I can just add them. Now in the next step, I get n times the variance of x, because the variance of all these terms are same. And why? Because they are identically distributed. right? So this is again equal to n times sigma square, and I have got my variance here. So what I just proved is that sigma x follows a normal distribution with the mean n mu and a variance n times sigma square. Okay, this would imply that if I talk about the mean, the mean is nothing but x bar. X bar is will have a distribution same as sigma x divided by n. So if I talk about this would approximately, I'm sorry, these are approximate distributions, so I have to put this sign here. So approximately it follows a normal distribution of mu comma. Now since this term has been divided by n, I'll have to divide the variance by a term of n square, because we know that variance of x upon n is same as variance 1 upon n square variance of x. So I'll have to divide this term by n square. So I'll have a n sigma by n term here. So this is the distribution of the mean. And how can I infer this? There is an inference to this definition. There is an inference to this definition. The mean of the sample mean x bar is mu, which is the same as the mean of x. This is the same as expectation of x. But the standard deviation, this is SD of x divided by n. This shows that when I add up a lot of variables, the mean standard deviation is actually reduced by a factor of n. So this can be interpreted very easily. Say I have these random variables x1, x2, x3 up till xn. The randomness in them, when I combine them, the randomness in their mean is cancelled out by all of them. If I get a very high value of this and a very low value of this, and then this has a high value and this has a low value, so if I have all these values, in the mean term these values cancel out, they cancel each other out. This low cancels out with this high and this low cancels out with this high. So the overall average, the variation reduces. And thus the standard deviation reduces. Now this all happens when n tends to infinity, that is for a very large sample. Now you will ask me that what is large? Now this is a very relative question. I cannot tell you what exactly is large. In statistics, we usually follow this practice of calling a sample large when it is greater than equal to 30. But in case of this particular thing, you can apply the central limit theorem whenever x is greater than 30 in the exam questions. But in practical life, the term large actually depends on the randomness or the skewness. It depends on the skewness of the sample. The skewness might be eliminated in 10, n is equal to 10 for 10 values, or it might even extend up to n is equal to 100. If the skewness is too much, we would require a very large sample to eliminate it. And if the skewness is less, we can eliminate it with n is equal to 10 itself. So it is very relative in real life, but for exam purposes you can take n greater than equal to 30 to be a large sample, and you can apply the law of large numbers, all the central limit theorem. Thank you. I guess I committed a bit of a mistake up here, so I would like to correct that. The distribution of the mean would be mu comma sigma squared by n. That would be the distribution. So we keep the variance here, and hence the standard deviation, which is the root of the variance, would be the standard deviation of x divided by the root of n. So I will rewrite this distribution again for you guys. So x bar follows a distribution of normal of mu comma sigma squared by n. So the variance is reduced by a factor of n, and if I talk about the standard deviation of x, it is standard deviation of x bar, it is the same as sigma, which is the standard deviation of each x divided by root n. Okay, so this obviously is an approximate distribution of the mean, so I put this sign here instead of the normal sign. To highlight that again, this is the sign for x follows normal distribution, and if I put in two dots here, this is the sign for x follows an approximate normal distribution with mean mu and variance of sigma square. So how do I use this? How do I apply this? That is what I need to learn next, and then I'll be discussing this small example from the core reading. So first thing I need to know is how do I apply this? I know that sigma x follows a normal distribution with the mean n mu, an approximate normal distribution with a mean n mu and variance n sigma square. So this would imply that sigma x minus n mu upon root over n sigma square will follow an approximate standard normal distribution. I've just converted this thing into a standard normal distribution by deducting the mean here and dividing it by the standard deviation. So this would have a 0,1 distribution, so a standard normal distribution. Similarly for the mean, if I talk about the mean, x bar follows a normal distribution with the mean mu and a variance sigma square by n. So similarly again, x bar minus mu upon root over sigma square by n will again approximately follow a standard normal distribution, that is n 0,1. So that is how I use it, and then I take the z value and then I approximate the probabilities using a standard normal distribution probabilities which are given in the actuarial tables. So let's consider an example. Let's solve an example here, and then you will be clearer on things. Okay, so I've got this example here. It is from page 3 of the chapter Central Limit Theorem or in the code reading. So this is the question. It is assumed that the number of claims arriving at an insurance company per working day has a mean of 40. So I've got a mean of 40. So mu is equal to 40 and a standard deviation of 12. So sigma is equal to 12. A survey was conducted over 50 working days. So I've got an n of 50, which is large. So I can use the CLT here. So I've got an n of 50. Calculate the probability that sample mean number of claims. Now they are talking about the mean number of claims. So I have to get the distribution of x bar of the claims arriving per working day was less than 35. So I've to talk about x bar, and I have to find that the mean number of claims, the probability that the mean number of claims are less than 35. So I'll solve it here. So what I have to find is that probability x bar is less than 35. Now I know that x bar has this distribution, so I can just write this as probability that x bar minus mu, that is 40, divided by sigma by root n, that is 12, divided by root over 50. This thing is less than 35 minus 40 over 12 over root 50. So this is what I have here. Then I just convert this into a standard normal distribution. So I've got a probability that z is less than minus of 2.946. And if I check this value from the tables, if I want to find this value out, this would be nothing but 0.00161. This is the value. So that is how I solve it, and that is the answer given in the core reading, chapter 8, Central Limit Theorem. Example is on page number 3. So the central limit theorem can be applied to any distributions. If I want to find the distribution of sigma x, or I want to find the distribution of x bar, okay, any distribution. But there are a particular few cases given in the core reading, so I am going to discuss them. The first case that is given is of a binomial distribution. So if I have a binomial distribution, if I have x, a Bernoulli random variable, following a binomial distribution with the parameters 1 comma theta. So this is a Bernoulli random variable, as it has a 1 here instead of n. If I will take a sum of n such random variables, if I will have a sigma x where I goes from 1 to n xi, it will have a binomial distribution. All these random variables will add up, and it will have a binomial distribution with parameters n comma theta, right? This can also approximately be estimated using a normal distribution, applying the central limit theorem. So how will I do that? In case of this, we know that sigma x has an approximate distribution of normal n mu comma n sigma square. Okay, the value of mu for each x is nothing but, if I want the value of mu, it is nothing but n theta, as n is 1, it would just be theta. If I want the value of sigma squared, that would be nothing but n into p into q. So that is, as I have a 1 for n, that would be theta into 1 minus theta. So this is the value of sigma squared. Okay, so this will approximately follow a distribution with n mu, that is n theta, and a variance of n theta into 1 minus theta. So this is the approximate distribution that I have here, and I can use this distribution to estimate the binomial probabilities if I have a sufficiently large n, that is if n is greater than equal to 30 for all practical purposes. So this is how we can estimate the binomial distribution using a normal approximation. If I talk about the Poisson distribution, next in line is Poisson. So if I have an x following a Poisson lambda distribution, I can approximate the probability of sigma x with the help of a normal distribution, obviously with the mean n lambda, because that is the mean of a Poisson distribution, and n lambda again, because that is the variance of a Poisson distribution. You can find these two out in the tables. So as the mean is lambda and the variance is also lambda, I can estimate the distribution for this. Similarly, I can have an x bar distribution here. X bar would follow a normal distribution with again lambda comma a lambda upon n. So that is how I can estimate the mean of a Poisson distribution using an approximate normal distribution. How did I find this? I just divided these two things, this by n and this by obviously n squared, as I had proved earlier. So that is how it works. If I talk about a gamma distribution, we know gamma distribution is nothing but the sum of exponential lambda distributions. So if I got I have a lot of exponential lambda distribution. If I've got n of these, they will add up to a gamma n comma lambda distribution. That is how it works. The alphas just add up. So I can also approximate this again. I can have a normal approximation with n instead of mu. I will have a lambda here, because 1 upon lambda is the mean of an exponential distribution, comma n by lambda squared. So that is the approximation for a gamma distribution. If I wanted for the mean, this was for sigma x. If I want an approximate distribution of the mean, it would be nothing but n of 1 upon lambda. This is for an exponential distribution's mean. So 1 upon lambda, and I will have nothing but 1 upon n times lambda squared here, because I just divided by n squared. The next thing we discuss, and this is the last topic from this chapter, this is called as continuity correction. So I am gonna discuss this right now. So what does continuity correction mean? What we are doing in this chapter is that we are taking distributions such as binomial and Poisson, and we are approximating them using a normal distribution. That is what we are doing. There is a problem here. The problem here is that the probabilities under a binomial or a Poisson distribution are discrete, and that under a normal distribution are continuous. Thus there is a need of correcting the continuity here. We need to correct the continuity. What does that mean even? Let's see. If I want to find the probability that x is equal to 4 under a discrete distribution, it would be meaningless to find the probability that x is equal to 4 under a normal or a continuous distribution, because x equal to 4 would just be an integration from 4 to 4 fx dx, which would be nothing but 0. So this is a meaningless result. What we need to do is we need to correct the continuity of this distribution. In order to do that, here x can take only integer values. So we can make these integer values to, in case of a normal distribution, we can make them include a range. For example, the range of 4 can be from 3.5 to 4.5. How did I get that? I just fixed it. I just fixed the continuity of this thing. Let's say I had a value at 3, and then I have a value at 4, and then I have a value at 5, and then 6. But if I need these to be continuous, I will have to take the values at 3 almost halfway. and then the values at 4 halfway, and then the values at 5 halfway. So the values at 3 would include from 2.5 to 3.5. The values at 4 would include again from a 3.5 to a 4.5. At 5 would be from 4.5 to a 5.5, and that is how you do a continuity correction. So for example, if I have got a probability that x is less than 2, if x is less than 2, this needs to include all the values that are less than 2, and it does not need to include 2. So 2 extends from 1.5 to 2.5, right? So I just need to get all the values before this 1.5. So this would be same as if I do a continuity correction, the probability that x is less than 1.5, and that is how I get it, because I had to exclude 2. Taking another example, if I want probability that x is less than or equal to 2, now I want to include 2 in this segment 2, so I want 2 included. So this would be the same as probability that x is less than 2.5, because now I want all the values less than and equal to 2, so I want 2. So I would take the entire range up to the last value of 2, that is 2.5. Okay, if I want let's say if I'll take just one more example. If I've got something like this, I need to correct for both. I want all the values greater than 3, so I would say I want all the values greater than 3.5. I do not want to include any values at 3. And then for 5, I want to include 5 and all the values lesser, so this would just be all less than 5.5, because I want to include 5, right? So that is how a continuity correction works. So whenever you are converting a discrete distribution, and remember this, the initial distribution should be a discrete one, into a normal approximation, you need to apply continuity correction. So the most important thing here to note is that if I have a continuous distribution such as a gamma or a beta distribution, and I want to approximate the probabilities using a normal distribution, I do not need continuity correction. This thing, continuity correction, is not applicable, because this is already a continuous distribution, and normal distribution is also a continuous distribution, so no continuity correction is required. Now I'm going to discuss one last example question here. This is question number 8.8 of the core reading. So we are going to discuss this, solve this, and then that would be all for this video. Okay, so the question here says that the probability of any given policy in a portfolio of term assurance policies lapsing before it expires is considered to be 0.15. So I've got the probability as 0.15. This seems to be something like a Bernoulli trial. So for each individual policy, I've got theta is equal to 0.15. And in a group of 100 policies, so I've got a n is equal to 100. Calculate the approximate probability that more than this is greater than 20 policies will lapse before they expire. So I need a probability that the number of policies that lapse, let's call it L, is greater than 20. So now I need a continuity correction here, because this is obviously a discrete thing, a Bernoulli trial. So I need L that is greater than 20.5. That is what I need. Now the next thing I do is that I need to find the distribution of this thing. So I need to approximate the mean and the standard deviation. Right, that is what I need. So the mean would be 100 into 0.15, and the variance would be 100 into 0.15 into 0.85 n mu and n sigma square, obviously, right? So this is the same as the probability that z is greater than 20.5 minus 102.15 is 15 upon root over this thing. So this is equal to 12.75. That is the value. Now I need to find the answer of this. So this is probability that z is greater than is 1.540, which is equal to nothing but this is 1 minus phi of 1.54. This is equal to 0.06178. So that's all for this lecture, guys. Thank you, and there will be more of these CD3 complicated topic videos, and cheers.